All right, day 11. More on kinematics. Let's start with a picture of a cheeseburger because I'm hungry and I like cheeseburgers. All right, velocity. Velocity, as you know, is just displacement divided by duration as opposed to speed, which is distance divided by duration. Velocity has a direction, whereas speed does not. And recall that it's just the slope of the distance versus time graph, where you find your xf minus xi over tf minus ti. And note that this value for velocity is equivalent to the slope of a straight line to connect the beginning and final endpoints. What I mean by that is, let's do this color today. How about that? And that size. Okay, so if I were to connect these 2 points, and if my line was straight, I would take the final and ending points and be okay. Well, the average velocity is 5 centimeters a second. Well, yeah, that's true. The average. Wait, come back here. There we are. The average velocity is indeed 5 centimeters a second, but as you can see, we were moving much more slowly the first 4 seconds and a lot quicker the last 8 to 10 seconds because our velocity is getting steeper. And so when you find your average velocity, you're just finding it by the beginning and ending points, and it doesn't give you what's called the instantaneous velocity in between. And so when we graph it, we would get a slope of y equals 5x if we start at the origin, connecting the beginning and ending point. And that's what you did kind of with the ticker tape. You started with the beginning and ending point and found, okay, well, this is my average velocity. Whenever you calculate the average velocity, like I said, you're finding the average for the entire motion and not in between. But what if we wanted to say find it for the first half and the second half of the motion? Well, that's where our next graph comes in. As you can see from the graph, the average velocity for your first half is around 2.5 centimeters a second. Or for the second half, it's 7.5 centimeters a second. 25 comes from the y-intercept. And the fun fact about that is if I take 7.5 plus 2.5 and divide that by 2, I get 5. And now I'm going to add the units, centimeters a second, which was our velocity of the beginning and end points. And so when I average those two sections, the first half and the second half, if it's perfect uniform acceleration, key on uniform, it's going to actually average out to be the average velocity of the whole thing. Now, what's the advantage of this? As you could tell, this more closely hugs the graph and is more accurate than this because, it varies here, and then it comes back up and meets, whereas here, it's a lot closer. It's hugging a lot more. This is getting more closer to the instantaneous velocities. If we break it up into smaller chunks, we can have a better idea of what velocity was moving at a certain point. I now can safely say, okay, it was moving around an average velocity of 2.5 centimeters a second the first 5 seconds and 7.5 the last 5 seconds. So you can get a more accurate detail of what's going on. And as I said, an average velocity for the very short duration, let's say we just kept breaking it up into chunks. I broke this up in half. And so I would do, these 3 points, and then those points, and then those points, and those points. You get smaller and smaller until you're finding what's called the instantaneous velocity. And that's for the average velocity for a very short duration. From calculus, it's the derivative. If you know the function. If you don't have calculus, it's not. You don't need to know that. I'm just throwing that out there just in case. And it represents the velocity that an object has at a single instant in time. And so we would need to know, for example, my mind blanked on him. He just ran the speed record. Usain Bolt, well, relatively speaking, soon. They want to know his instantaneous velocity on how fast he was running, if they're trying to see if he broke the record for a human speed, not what his average is, which is what it's measured when he does the 100-yard dash. And the instantaneous velocity would be tangent to the line at that given point to the curve. And so this would be like your composite of your position versus time, and the instantaneous velocity would be right when it right where it lies tangent to that curve. And so that's what you're doing. You would be finding a smaller and smaller portion until you're actually literally just lying tangent to that curve at that point. So if we're able to find the instantaneous velocity at the beginning of the motion and the instantaneous velocity at the end of the motion, then we can just average the two. And this is what we used to solve a lot of our problems, that the average velocity is the initial plus the final divided by 2. I will generally write that as V is equal to VI plus VF over 2 with capitals instead, because it's a little bit easier to write. And then we also still know that the average velocity is delta x equals the average times time. And so if we make a substitution, we get an equation that's quite helpful. This equation still does average velocity, but what's more important is that we may not know the average velocity. We just may know two different velocities at two different points. And so we can use those two velocities to get a measure of possibly displacement or time depending on what the problem is going to ask. And so this is the equation we're going to be using for the next day or two until we add another aspect to it, which is going to happen. Okay, pronghorn problem. Pronghorn are the fastest land mammals in North America, around 63 miles an hour. They evolved when we had some sort of ancestor of the cheetah, which doesn't exist anymore, but pronghorns still do. Yay. Let's say you pass a pronghorn traveling at 10 meters a second. That's the pronghorn speed. You are traveling at 18 meters a second. The pronghorn doesn't like it and catches you because they're fast in 10 seconds. We want to know the pronghorn's final velocity and how far it travels. Well, we know that from previous slide, delta x is equal to vi plus vf over 2 times delta t. The problem is we do know the time, but we don't know the distance or the final speed of the pronghorn, so we can't use that. We can figure out how far it travels and then come back to the final velocity, because we know that you being the driver, I guess in this case, and the pronghorn go the same distance. So I could say, okay, well, delta x is equal, and you are traveling at 18, so I could say 18 meters a second times 10 seconds, seconds cancels, that's going to give you 180 meters. And we know that the pronghorn is going to travel that, so I'm going to plug that back in. 180 meters, its initial velocity is 10 meters a second, plus its final, we don't know, divided by 2, all times 10 seconds. All right, so let's multiply both sides by 2. That's going to give me 360 meters and distribute by 10. It's going to give me 100 meters, since my seconds are going to cancel, plus VF times 10 seconds, or 260 equals 10 seconds times my variable of VF. Divide the two out, that gives you meters over a second, or 26 meters a second is going to be my final speed. Or, sorry, in this case, velocity. That's a little unrealistic. Well, no, that's actually realistic. They can go about 26. That's on the very high end, but it can happen. So this is similar to the last problem from, I think, Lab 11, but it's slightly different in how we set it up. All right, that is it.